Hello everyone, I am Mohammad Ashfaq, a master's student from School of Computer Science and Communication Engineering, Jiangsu University. In this presentation, I shall introduce a new method to increase the efficiency of fixed size candidate set adaptive random testing using SIMD instructions. I shall first give the overview of software testing, adaptive random testing, especially fixed size candidate set adaptive random testing. Then I shall discuss the efficiency problem of ART. To solve this problem, I shall describe our key observation, which can be taken as the motivation of this paper. After this, I shall give an overview of SIMD instructions. Then the main framework, which is called as FSCS-SIMD, will be introduced. In the end, we shall discuss the results and then we shall conclude the presentation. What is software testing? Mayers defines software testing as the activity in which we execute software with the intention of finding faults in it. We execute software by giving it some inputs which are called test cases, and if the outputs of software is not according to the expected output, we can call that there must be something fault bug in a software. There are many software testing techniques which can be broadly categorized into black box testing, white box testing, and gray box testing. In white box testing, the underlying code and logic of the software is analyzed. However, we are more interested in black box testing, where we focus on the input-output behavior of software for finding faults without going deep further into underlying structure and code. In this way, testers get the freedom to test software developed on a wide variety of technologies and programming languages. As software input domain can be extremely large and it is impossible to exhaustively test software against all inputs, there are some techniques exist to deal with it. For example, random testing is a popular and widely used black box testing technique that randomly generates test cases from the software input domain. Software is run by giving those selected inputs and the process is repeated until a termination criteria is reached. Adaptive random testing. Adaptive random testing, abbreviated as ART, is an enhancement of random testing which works on the motivation that failures in a software tend to cluster themselves in contiguous regions. As we can see in the figure, that failure regions of a software that accepts two inputs can be categorized as block, strip, and point failure pattern. ART works on the principle that if a test case is unable to find failure, it is high probable that its nearby test cases will also be unable to find failure. Therefore, the next test case should be selected that is far away from previously executed non-failure causing test cases. There are several methods of ART developed on many intuitions and observations. One of them is fixed size candidates set, FSCS. FSCS version of ART is distance-based ART method that uses the notion of distance between executed test case set and candidate test case set. During the testing process, FSCS keeps two test case sets that is called candidate test case set denoted as C and executed test case set which is denoted by E. In its test case generation process, FSCS randomly generates a fixed number of candidate test cases and selects the candidate which is farthest from all previously executed but unsuccessful test cases. In other words, the nearest neighbor of each candidate test case is determined by calculating the distance between all elements in E. Finally, the best candidate test case is selected as the candidate whose nearest neighbor is farthest away. As an illustration, please have a look at figure 2a, where three black dots represent executed test cases and two circles represent the candidate test cases. These candidate test cases are randomly generated across software input domain. To select best candidate test from them, the nearest neighbor of each candidate test is determined, as shown in figure B. The nearest neighbor of C1 is T2 and the nearest neighbor of C2 is T1. As we can see that the nearest neighbor of C2 is farthest away from as compared to the nearest neighbor of C1. Therefore, C2 will be selected as the next candidate and next test case as shown by T4 in figure C. And this will be executed in the next testing iteration. In this way, ART leads to spread test cases more evenly in the software input domain, which increases the probability of selecting test cases from failure regions. To see the difference clearly, please have a look at regions 1 and 2. We observe that there are no test cases produced in region 1 by random testing, whereas we have 12 test cases in region 2 with the same size. On the other hand, FSCS maintains its even spread of test cases across the software input domain. However, although FSCS is a well-known ART method and has been widely used in many real-life testing applications, it faces some severe efficiency problems. As shown in algorithm 1, it can be seen that the statement 4 is executed number of size of candidate test case set multiplied by size of executed test case set. If size of executed test case set is, let's suppose, 1000 and size of C is n, which is usually 10, the statements 4 will be executed by 10,000 times. So this leads to two main problems. One is the distance calculation redundancy, which means that the same set of arithmetic instructions for distance calculation are given to CPU again and again whenever two test cases from C and E are loaded to CPU. By one fetching, we mean that test cases from C and E are processed sequentially. At one iteration, only one test case from C and one test case from E is loaded into CPU for distance calculation. Both one-by-one fetching and distance calculation redundancy are the characteristics of single instruction, single data CPU processing architectures. Hence, the current implementation of FSCS follows SISD architecture, and this is the main reason for its low efficiency. What is now we propose to use of instead of single instruction, single data, we propose use of single instruction multiple data to increase the efficiency of FSCS-ART. SIMD instruction architecture increases the processing capacity of processors by performing multiple computations in a single instruction. These instructions are often called vectorized instructions because we can think of them as operating on vectors of values. Almost all CPU vendors provide SIMD technology in their processors. For example, Intel machines provide SIMD technology in MMX, SSE, SSE2, etc. Similarly, AMD processors provide 3D Now, Enhanced 3D Now, and other SIMD architectures. As an example, suppose we want to add elements of two test sets X and Y and store into set Z. In ordinary setting, 8 instructions will be needed to load elements of X and Y from memory into CPU registers. Moreover, 4 instructions are required for the addition operation. As a result, the whole process requires 12 instructions. However, if we use SIMD, all 8 values, 4 values of X and 4 values of Y could have been loaded into CPU register by using only 2 instructions. After this, all the values will be added using a single addition instruction. In other words, addition can be performed simultaneously on all 4 values of X and Y. In this way, the task that was naively done by 12 instructions can be performed by only 3 instructions. We propose that if we can be able to avoid time consumed in one-by-one loading and candidate set test cases and executed test cases into registers and avoid redundant distance calculations given to CPU, the time overhead of FSCS would be marginally reduced, still preserving its original failure detection effectiveness. The primary motivation for the application of SIMD instructions into FSCS is that in the phase of generating a new test case, executed test case set remains pristine. In other words, there is no change in E while generating a new test case. Consequently, we can convert E into SIMD readable data types and calculate nearest neighbor of each element of C from E in a parallel way. In short, we aim to boost the efficiency of FSCS algorithm by changing its implementation from SIST to SIMD architecture. This is the framework of FSCS-SIMD. As we can see, the whole process is summarized into 9 major steps. The first step is the initialization phase, where a candidate test case set, executed test case set, a matrix of all distances called dist matrix, and distance calculation function translated into SIMD instructions are defined. If there are n elements in C and m elements in E, the rank of distance matrix will be n cross m. The process of translating a distance function into SIMD instructions mean that using SIMD intrinsic for programming distance function so that only one unique distance calculation instruction can be applied to a batch of elements of E, C, and E fetched into SIMD registers. In step 2, a randomly generated test case from software input domain is executed and added to E. Then the termination criteria is evaluated. If the termination criteria is not satisfied, the algorithm moves to step 3. And n number of candidate test cases are randomly generated, preferably with uniform distribution from software input domain. The number of candidate test cases are generally 10 in most ART studies. The primary process of SIMD spans from step 4 to step 7. In step 4, C and E are converted into SIMD data types. In step 5, dist matrix is generated by all pairwise distances of C and E using SIMD. This step is the most important in terms of time overhead reduction. In step 6, the minimum value in each row of dist matrix is found and stored. This value on each row represents the minimum distance of each element of C. For example, the minimum distance on the first row represents the nearest neighbor distance of the first element of C. In step 7, the maximum value from all minimum values found in step 6 is found. This value represents the candidate's nearest neighbor, that is at the furthest distance from the nearest neighbors of other candidates. This corresponding test case from C is selected as the best candidate test case, C best. In step 8, the best candidate test case is executed and added to E. The process from step 3 to step 8 is repeated until the specified termination criteria is reached and E is returned, which is the final step. This is the workflow of algorithm. In the first step, let's suppose there are some test cases in executed test case set and candidate test case set has 3 candidates. These are converted into SIMD data types. Then distance matrix is generated, which includes the distance. Delta represents the distance, Euclidean distance between the test cases. Then the minimum distance is the minimum element in all the rows of the distance matrix. Min row 0, min row 1, min row 2. Then the maximum distance is basically the nearest neighbor that is farthest away would be the maximum number in the row of minimum distances. Then the candidate index will be found, the position of max distance in the distance matrix, and that test case index would be returned as the best test case. This is the sample data in the real world working of the algorithm. We can see some elements E is populated with some elements and C is also populated. This is the distance matrix. On this row we can see the minimum value 0.34, 0.29, 0.41, and then the maximum value from them is calculated. Then 0.4 index of 41 is 0.41 is this second row, second column. Basically it is third row, but we are calculating from 0 index, and then it means that the candidate 2, 0, 1, 2, this candidate would be selected as the best test case. The experimental setup of our algorithm includes 2 research questions. One is related to effectiveness and other is related to efficiency. Effectiveness: thus, does FSCS-SIMD successfully preserve the failure detection effectiveness of the original FSCS algorithm? Step 2 is, how efficient is FSCS-SIMD in relation to FSCS? To evaluate the effectiveness, we use F-measure, which is the expected number of test cases required to find the first failure in a software. Which is lower the better. F ratio is the ratio of F measure of ART to the F measure of RT. Basically, this shows that how much effectiveness of ART is better than the effectiveness of random testing. Efficiency is calculated by using test case generation time, the time required to generate a given number of test cases. Less test case generation time leads to better efficiency of a method. The results of the evaluation consists of 2 parts. One is simulations and second is empirical studies. Both parts have the effectiveness results and efficiency results. The effectiveness results is shown in this table. You can see that the theta represents the failure rate of the program, simulated failure rate, and block, strip, and point failure patterns are simulated in 2-dimensional input domain. We can see the results of F ratio results of FSCS and FSCS-SIMD are basically almost the same in all failure patterns. Therefore, both methods show similar failure detection effectiveness, and the difference between F ratios of both methods is not statistically significant. In other words, our proposed method, FSCS-SIMD, preserves the failure detection effectiveness of FSCS. In terms of efficiency, we can see that the table is plotted and in 2-dimensional and 3-dimensional input domains, and these are the n is the number of test cases generated, and this is the time taken to generate this number of test cases using FSCS and using FSCS-SIMD. We can see in the graph is plotted here. We can see in the beginning test case generation time difference is small, which starts becoming obvious when the number of test cases increase. For both two-dimensional and three-dimensional input domains, the cost reduction by FSCS-SIMD is 85 to 87% when n is less than 100. But after that, this time cost reduction goes up to 93 to 95%. Test case generation time for both methods increase when we move from dimension 2 to dimension 3. Empirical studies are conducted on 12 real-life programs whose details are given in this table. In terms of effectiveness, we have tested these programs by using RT, which is random testing, FSCS and FSCS-SIMD. We can see that the F measure of RT is always more than the F measure of FSCS and FSCS-SIMD. It means that the effectiveness, failure detection effectiveness of FSCS-SIMD and FSCS is much lower than the random testing. Both FSCS and FSCS-SIMD show similar F measure and F ratio values, which is according to the simulation results. Efficiency results of empirical studies are shown in this table, where this is the test case execution time taken to execute a test case. We can see that the test case execution time is much lower as compared to the test case generation time. Therefore, the reduction in test case generation time is very essential. There is no wonder that random testing shows the best case test case generation time, because it has nothing to deal with to calculate the distances between test cases. However, the test case generation time of compared with FSCS-SIMD shows time cost reduction, which is more than 90% with average value of 94%. The most notable differences are in program cell, SNCNDN, and PLGNDR, where the efficiency improvement is more than 95%. Conclusion. In this paper, we proposed fixed site candidate set using single instruction multiple data architecture, which harnesses SIMD features of machines to boost the efficiency of regional FSCS algorithm. FSCS-SIMD relieves the distance calculation overhead by calculating multiple distances simultaneously using parallelism and distance calculation functions translated into SIMD intrinsic. FSCS-SIMD reduce the test case generation time to 90. In future works, we will add more real-life program, more comparison methods, and implementation of FSCS, SIMD, and other programming languages besides Python. Same idea can be applied to other ART strategies rather than FSCS to increase their efficiency. Beside Python, SIMD technique should also be analyzed in the other dynamically typed languages where original implementation of ART methods is prohibitively slow. Besides ART, the paper may provide inspiration for similar optimizations in different testing algorithms. Thank you everyone.